Welcome back to Differential Calculus. In this video, I want to talk about the power rule, which is the first of several rules we're going to be looking at in the process of differentiation. Let me get my head out of the way and let's define a few things. First of all, recall that for a real valued function f, the derivative of f at a point C is denoted and defined as f prime of C. And this is defined using a limit. The limit as x approaches C of f of x minus f of C all over x minus C. And for the sake of convenience, we also looked at this written as another form. If C happens to be equal to x plus some little bit delta x, we could also write this limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, right? That's just a substitution between those two definitions. They both are useful in different applications. The most important thing right now is that using this limit definition in order to find the derivative of a function at a point is an incredibly tedious process. It takes a while to go through. It's not fun to go through. And so it would be great if we had a more general tool at our disposal. That's what we're going to be looking at today. Differentiation is the process of finding a general expression for the derivative function. All right, there's a lot to unpack here, and a lot of it is subtle, but the vocabulary is important, and a lot of people get confused by it. So I do want to take the time to make sure that we have the vocabulary down before we get into the hows and whys. Differentiation is an operator. Differentiation takes a function and turns it into another function. The new function that results from the operation of differentiation is called the derivative. We can define the function by a limit that is a process of differentiation. But it would be better if we can find an expression, if we can find an algebraic form for our function. And in order to do that, I have two rules of differentiation that I want to show you in this video. I'm going to very quickly go through the process of using the limit to find that these rules hold true. I do not expect you to necessarily follow step by step, but I want to give you the general feel for what's happening here, because I think it's valuable to understand that this isn't just a fiat rule. This is the nature of the derivative that we've talked about forces these rules to be true, and these rules turn out to be incredibly convenient. All right, so the first one is linearity. Linearity tells us that if we differentiate a linear combination, some constant a times a function f of x plus some other constant b times some other function g of x, we are going to get a times f prime of x plus b times g prime of x. Linearity is a wonderful thing to have. When we have it, we celebrate. And this rule really follows almost directly from the linearity property of limits themselves. Starting with our limit definition of the derivative, we can rearrange all of the terms in the numerator to get everything involving f together, get everything involving g together. From there, we can split up the fraction. We can factor a out of the first fraction, we can factor b out of the second fraction, and then we can use the linearity of the limit to split this up. We're left with a limit in the first set of parentheses that is f prime of c, and we're left with a limit in the second set of parentheses that is g prime of c. So whenever we have a limit, whenever we have a derivative of a linear combination, we can split it up. Again, I know I went through that quickly. I do not expect that you followed every single step and that you would be able to reproduce this. But I wanted to show you that this comes from something. It's not just a magic black box. Linearity is an intrinsic property of the way we already defined the derivative. Right? And linearity is great if we know what the derivatives of the two functions f and g are, which I guess means we need to start looking at some more specific functions. Right? That does take us to the title of this video, the power rule. The power rule tells us that the derivative of x to the n power is equal to n times x to the n minus 1 power. And that almost seems too good to be true. The proof on this one is a little bit ugly, but it does work out. Again, I've said this a couple of times, I'm going to keep repeating it. Do not take the time to try to make sure you understand every step. I don't expect that you understand every step of the proof and that you can follow it clearly. But broad strokes, you should be able to listen to my explanation and understand step by step that I'm doing algebra that is perfectly reasonable and that this has to fall out from what we're doing. Right? So listen to what I'm saying. Don't worry too much about what I'm writing. I just want you to get the basic flavor of what I'm doing here. You can see for this one, I am going back to the delta x goes to 0 version of the limit definition of the derivative. And then immediately I do something that looks really crazy. X plus delta x to the n power. This is the binomial expansion. It follows Pascal's triangle or anything else you may have seen in the past. At the very least, you should be very familiar with the expansion. X plus b squared is x squared plus 2bx plus b squared. I have delta x instead of b, but the fact that there is a 2 here does in fact come from the fact that that is squared. If it was cubed, it would be a 3. In general, it's an n. And then there's something else, and there's my b to the second power, and it continues down the line from there. I don't really care about everything else, because as you'll see in just a moment, a lot of stuff is going to go away. Specifically, the first thing that's going to go away is I have a plus x to the n and a minus x to the n that just cancel each other out. And then what I'm left with is a bunch of terms in the numerator that all have at least one factor of delta x. I can cancel that one factor of delta x with the delta x that's down here. So that delta x goes away. This becomes delta x to the first power. The next one will be delta x to the second power, and so on. And then the key to all of this is that every factor, or every term that's left, except for the first term, has at least one factor of delta x in it. And as delta x goes to 0, each term that has a delta x in it goes to 0, leaving me with n times x to the n minus 1 power. Again, I know that that is crunchy algebra. Again, I want to stress that I do not want you to take the time to try to master the crunchy algebra. That's not the point of this. The point is to be able to follow the verbal argument. I'm going to write the limit definition. I'm going to use binomial expansion to expand out that power. If you don't know how that works, that's not important. All that matters is that you accept that it does work. I'm going to cancel out a whole bunch of delta x's, and there's only one thing left that doesn't have a delta x. That's the process that we're focusing on here. All right. And now we have the two rules, linearity and the power rule. Together, those two rules allow us to take derivatives incredibly quickly. So if I have a function, f of x is 3x squared plus 5x minus 4, and I want to figure out f prime of 1, I could go back to that limit process that we've learned previously. It's tedious, it's annoying, I don't want to. So instead, I use the differentiation rules that we've just established. The derivative of 3x squared plus 5x minus 4 by linearity is 3 times the derivative of x squared plus 5 times the derivative of x. And then this last one's a little bit interesting. 4 is a constant. It's not a function of x as it's written. So I'm going to use a trick of algebra that you've seen many times in the past. X raised to the 0 power is 1, and 1 times anything is that thing. So 4 is the same thing as 4 times x to the 0 power, and then I can use linearity to split it up, bring the 4 outside, leave the x to the 0 power in the differentiation. And for each of those derivatives, I can use the power rule. The derivative of x squared is going to be 2 times x to the 2 minus 1 power. And for this example, I'm going to write these out. In general, you don't need to do that. As you get more comfortable with these, you're going to learn that you can basically skip all of the intermediate steps. But for the first example, I'm writing things out in as much detail as I can. The second one, the derivative of x. Again, not immediately obvious, but if I think about that as x to the first power, then I can see that n is 1, and I'm going to get 1 times x to the 1 minus 1 power. And then for x to the 0, I will get 0 times x to the 0 minus 1 power. All right, 3 times 2 is 6. 2 minus 1 is 1. 5 times 1 is 5. 1 minus 1 is 0. And then in the last term, we have 0 times a whole bunch of stuff, which is just going to end up being 0. We don't have to worry about anything else. One more bit of cleanup. X to the first power is just x. X to the 0 power is 1, and multiplying anything by 1 doesn't change it. So I can write this as 6x plus 5. Right? This is my derivative function, f prime of x. And if I wanted to evaluate f prime of, I've already forgotten, f prime of 1, I can just evaluate this function. 6 times 1 plus 5 is 11. I know this particular example made that seem like a whole bunch of work. But with just a little bit of practice, I promise you that you're going to quickly get to the point where you can go straight to the end there without writing out any of the intermediate steps. It takes a little bit of practice, but once you have it, you will have it. It will be muscle memory that you can do without thinking about it. Let's take a look at another example like this. G of x is 4x cubed minus 2x squared plus 5x minus 7. And here we're going to look for a general expression, g prime of x. So out of laziness, I'm not going to write out the whole set of rules for differentiation, but I am going to write a little bit more than is strictly necessary. Again, as you get comfortable with this, you will learn to skip this step. But I know, by linearity, I am going to have 4 times the derivative of x cubed. Using the power rule, n is 3 in this case. I'm going to get n, which is 3, times x to the 3 minus 1 power. The derivative of x squared, n is 2, so I'm going to get 2 times x to the 2 minus 1 power. 5x, n is 1, so I'm going to get 1 times x to the 1 minus 1 power. And remembering what happened with the constant last time, and the fact that I'm running out of space on the screen, I'm going to remember that the derivative of a constant ended up as 0, and that's just a rule that will always happen. You always write it as x to the 0 power, which means it's going to be 0 times stuff, and it doesn't matter what the stuff is because you're multiplying by 0 and the result is 0. But just a little bit more cleanup from here. 4 times 3 is 12. 3 minus 1 is 2. 2 times 2 is 4. 2 minus 1 is 1, and we generally don't write the power of 1, we just call it x. And 5 times 1 is 5, 1 minus 1 is 0, and again, x to the 0 is just 1. 5 times 1 is just 5, so we don't have to write anything else out. All right, so again, as we get comfortable with this, we start skipping steps. We write a little bit less each time until you get to the point that you can just write that out when you're asked to find the derivative of a polynomial, and you don't even have to think about it. let's take a look at, I have two more examples I want to do in this video. And I'm going to use some relatively simple examples. H of x is the square root of x. It's not immediately obvious that you could evaluate the derivative of the square root of x using the power rule, but if you remember that the square root of x is x to the 1/2 power, now we've got that n is 1/2. And we can use the power rule. There's nothing in what we stated about the power rule that said it had to be a whole number. So h prime of x is going to be n, which is 1/2, times x raised to the 1/2 minus 1 power. All right, 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. Now remember, properties of negative exponents. X to the negative 1/2 is 1 over x to the positive 1/2, and x to the 1/2 power is the square root of x. So the derivative of the square root of x is 1 over 2 times the square root of x. All right? Things are getting a little bit more interesting now. Related to that one, I don't have enough space. Let's get some clear space. How about k of x is 1 over x cubed? We were just talking about the negative powers rule, and that's what I'll use here to rewrite that k of x is x to the negative 3 power. If n is negative 3, k prime of x will be negative 3 times x to the negative 3 minus 1 power. Negative 3 minus 1 is negative 4, and I guess it would be a good idea to rewrite that using a positive exponent, negative 3 over x to the 4th power. All right? So we can use the power rule when we have fractional exponents by just rewriting it and going from there, right? Rewriting radicals using fractional exponents, using the power rule as it's defined. We can use the power rule for negative exponents, writing 1 over x to a power as x to a negative power. Using the power rule, we don't have to do anything weird or different. We just have to not panic. All right. I would like you to take a couple of minutes and see if you can put all of that together. I would like you to try to look at the function f of x equals 2x to the 5th plus 3 over the square root of x minus 11. And see if you can find an expression for f prime of x in this case, right? F of x is 2x to the 5th plus 3 over the square root of x minus 11. All right, take a few minutes to see where you can get with that one, and I'll see you in the next video.